Welcome back to our series of lectures on reinforced concrete design. In this topic, we'll discuss how to use charts for the design of singly reinforced concrete beams. Charts are developed for dimensionless quantities and therefore they can be applied to all sizes of beams and any material properties. The dimensionless quantities include the following: K, which we know equals the moment divided by BD squared times FCK, and the area of steel, AS, times Fyk divided by BD times FCK. As you can see, we get a Z to D ratio and an X to D ratio, which means that everything is dimensionless. The charts are derived for the range of values for the X to D ratio. In this lecture, we'll see how charts are developed for the rectangular stress distribution in the concrete compression zone. We'll be looking at the chart styles from the ICE, the Institution of Civil Engineers, and the IStructE, the Institution of Structural Engineers. First, we'll see how to develop the ICE Design Manual style chart. We'll start by considering the expression for moment, which we looked at in the previous lecture. Dividing this expression by B times D squared times FCK leads to the following non-dimensional relationship. The left-hand side of this relationship is the non-dimensional parameter K, while the right-hand side depends on the non-dimensional X to D ratio. Equilibrium of forces in the section results in the following equation, and dividing both sides of the equation by B times D times FCK and rearranging leads to the following non-dimensional relationship, where the right-hand side depends on the non-dimensional X to D ratio. Since the left-hand sides of these two relationships depend on the X to D ratio, they can be combined into a chart. The chart is developed for a series of X to D values and is shown here. As you can see, the abscissa is a non-dimensional quantity AS times Fyk divided by BD FCK. The ordinate is the non-dimensional parameter K. The chart can be used to design a new singly reinforced concrete section for a certain moment or to analyse an existing section for bending capacity. To understand how it works, let's consider the example given here. Assume a beam is loaded by a moment m, which gives the parameter K equal to 0.15. Now that these are known, we can find the required steel area. To do that, we draw a horizontal line at the level of K equals 0.15 until the intersection with a curve. From the intersection point, a vertical line is drawn until we find the intersection with the abscissa. This gives the quantity of Fs Fyk divided by BD FCK equal to, in this case, 0.203. From this quantity, the steel area AS and the X to D ratio can be found. Alternatively, in an existing section, the area of steel AS is known, and that can be used to find the quantity AS times Fyk divided by BD FCK, and then the parameter K and the maximum moment the section can carry. The chart developed by the IStructE is based on the same expression for the parameter K. However, the IStructE design manual additionally considers the Z to D ratio. The chart is also non-dimensional as it was derived for the non-dimensional parameter K and the non-dimensional X to D and Z to D ratios. The IStructE design chart has two curves which define the X to D and Z to D ratios for the parameter K. As you can see, the chart has two ordinates. The abscissa of the chart is the parameter K, while the left ordinate is the Z to D ratio and the right ordinate is the X to D ratio. To understand how the chart works, let's consider the following example. For K equals 0.6, we draw a vertical line till the intersection with the X to D curve. From the intersection point, a horizontal line is drawn until the intersection with the right ordinate. The corresponding X to D ratio equals 0.145. The vertical line is then continued till the intersection with the Z to D curve. From the intersection point, a horizontal line is drawn until the intersection with the left ordinate. The corresponding Z to D ratio is 0.945. From the parameter K and Z to D and X to D ratios, the area of steel can be found. Let's see how these charts can be used in the design of singly reinforced concrete sections. Let's look at the design that we previously solved in the last lecture. As a reminder, this is a beam with a 300 mm wide and 500 mm deep cross-section. The effective depth was 450 mm, there was a moment of 120 kN meters, the yielding strength of steel was 500 megapascals, and the compression strength of concrete was 25 megapascals. We needed to design beam reinforcement assuming 15% redistribution of moments. We start the design by calculating K. Substituting the values of relevant parameters, we find that K equals 0.079. For a 15% redistribution, the limit value of K is 0.168, and the limit for the X to D ratio is 0.45. From the ICE design chart, we can find that for K equals 0.079, the quantity AS times FYK divided by BD FCK is 0.099. If we rearrange that and substitute the geometric and material properties, the area of steel equals 668 millimeters square. The application of the IStructE design manual also starts with calculating the parameter K. Now we need to find the Z to D ratio from the chart for K equals 0.079. From the chart, we can see here that the Z to D ratio equals 0.922. Now that we have that, we see that it's smaller than the limit value of 0.95D, and therefore the lever arm Z equals 416 millimeters. Now we have that, the steel area can be calculated from the expression for moment. After rearranging and substituting the values for relevant parameters, we find that the steel area is 663 millimeters square. That is very close to the area of 668 millimeters square that we got from using the ICE design chart in the previous slide. Given the conditions imposed on the steel area by the diameter of manufactured bars, these difference results in the same design. And that concludes the design of singly reinforced concrete sections using design charts. If you're interested in learning about design charts for parabolic rectangular distribution stresses, please let me know in the comments and I will develop a lecture on alternative methods of design. Thanks for joining me.